Let's talk here a little bit about the end of the year stuff. Um, so again, we've already talked that we dropped the 2 homework quiz grades and the 2 homework assignment grades. That happened back when the seniors were still here. The last day for any incomplete or missing stuffs is going to be on the 25th. At this point, you guys have taken all of the tests. I know that I haven't posted grades yet for the Chapter 15 thing because we just did it and I haven't got them checked yet, but it's on my to-do list. But as soon as you might already be sure what you want to do, but as soon as you're sure, you can send me an email and let me know whether you want to do the doubled high test score or elect to do a retake. If you elect to do a retake, please send me the chapter that you're planning to retake. If you want to wait till the Chapter 15 stuff posts, that's totally fair. But if you know you're going to do a double and your 15 ends up being a better double, I can always, I'll make sure that I update it. Or if I forget, you can always remind me and it's not a big deal. If you are doing a retake, we're going to do them that week, that 3 day, sometime during that 3-day week. And we'll just schedule that on an individual basis. My hope would be to do that in class. The exam's going to cover chapter 7 through 12 and then 14 and 15. I have 80 total points, 10 points worth of questions, so 2 to 3. Some sections will be, some chapters, 2 kind of bigger questions, or like 1 really big question, 1 pretty small one, or 3 kind of small medium ones. But there's a total of 10 points from each chapter. As the same as last year, you can skip 2 questions on the exam as long as they're not in the same chapter. And then these exam questions will be variations on previous test questions. That is the same problem with different numbers or different conditions. And I'll provide you an old version of the chapter 12 and 14 tests that we're not going to take. And you can make a full sheet of notes for the exam. You can write on both sides, and those notes are due by the end of school on 5/23. Nothing later than that would be accepted. Exams start the next day. So if you want to turn that in earlier, that's totally fine. I'll put that no exceptions in at the end. Cool about, yes, Sid?
So the notes are due by
5:31, excuse me. Yeah, that's the very last day of classes before exams start. So the schedule here, this is not your guys's. I pulled the wrong thing. Excuse me real quick. This is such a Mr. Kulik move. I spent all that time like, oh boy. There we go, that's better. So, what did I do here? Oh, this is fine. I'm so stupid. This was fine. Okay. So, we're gonna do sections this Sunday, the problem set is, 131 to 184, and then the review. That's for this Sunday. That's the second to last problem set. The last problem set would be due essentially this Tuesday, the 24th or whatever. And that's going to contain these problems from chapters 14 and 12. So I just, instead of giving you all the problems on the problem set, I just handpicked some that I thought would be appropriate. So I think there's 20 or so total problems. Which seems like pretty doable in a week versus like, oh yeah, between the 2 chapters, there's like 96 problems or something. It's like, that seems a little excessive. Cool with that? Okay. My hope is to wrap everything up by the end of next week. The 3-day week where your juniors are also on retreats are just going to be exam review days. You can work on your notes or whatever, review things you need to. If you're doing a retake, you can do a retake on one of those days. And then the next, the Tuesday is another review day, and then your exam starts from there. Cool. Any questions about any of that stuffs? I think I got it all in there, right? Denise?
Do you know anything about the New Year retreat? Because we're all.
Other than you're going on those 3 days, I don't know. One of those 3 days you're going on. That's all I know. Okay. So let's get this show on the road, right? Chapter 14. We're going to be talking about rational functions. So when I say a rational function, what do I mean? It's something of the form P of x over Q of x, where those guys are polynomials. And Q of x is not 0. Okay. So the first big thing we want to talk about is the domain for rational functions. I'm just going to do this through an example. So what can happen if you have a division problem? How can that become undefined?
If the denominator is 0.
The denominator is 0. So that's the same thing we're going to care about here. Is we know that whatever that denominator is, it can't be 0, or else this function fails to be defined. So we know that x cannot equal 1/2. So our domain would be negative infinity to 1/2, and then 1/2 to positive infinity. Everybody cool with that? Can this get more complicated? Well, sure. What if we have something like this? Well, I still just care about the same things, right? But that can't equal 0. So to solve this, how would I want to do that? Great, yeah, so there's a greatest common factor. That's a great place to start. What now? Should be jumping out right at you, like it's the boogeyman. What? Is there something else we can factor here? Yeah, how does that factor? Yeah, that's great. So we factored that as much as we can now, right? So we just zero product property this, just like we would. So there's three places where we can't have that value, right? So what are the intervals that we can have? Well, negative infinity to the smallest one to the middle one to the biggest one, and then biggest one to positive infinity. Cool beans? Everybody cool? We're not going to worry about ranges for these because the ranges are cuckoo crazy and not or beyond the scope of what we'd be interested in doing in this class. So the next thing I want to talk about is the key features we'd need to include for a graph of a rational function. So we have the vertical asymptotes. Assuming they exist, they may not always exist, right? You may or may not have one, and you could have many. The end behaviors, sometimes those end behaviors will be, like horizontal asymptotic, and sometimes they'll be like something else. But those can be a little bit tricky. We'll talk a little bit more on how to identify what those are. In fact, we'll do it right now. So let's say we have this rational function. There's three cases that we could run into. One where the degree of the numerator is bigger than the degree of the denominator. In this case, we have what's called an oblique asymptote. And we find that using polynomial division. We'll go into detail when we look at some examples. In case 2, the degrees are equal. And this we have a horizontal asymptote or horizontal end behavior at y equals the leading coefficient of p of x over the leading coefficient of q of x. And case 3 is where the degree of the denominator is less than the degree of, the degree of the numerator is less than the degree of the denominator. And here, again, we have a horizontal asymptote or end behavior at 0. The next thing that we would want to include are the zeros. That's where the numerator is equal to 0. And maybe we should make sure that, let's say, just for the record on all these, that that r of x is the reduced fraction. And then we have y-intercept. And I guess my last thing I should put on here, I don't see it on this list though, but I'm sure it's there, are any removable discontinuity. And this could occur only from reducing. So if that fraction is reducible, we could run into one of these things. So let's do this for f of x equals x minus 1 over x squared minus 4. Everybody's cool? Okay. How do I find the vertical asymptotes?
So the denominator equals 0.
Yep. First, let's at least make a cursory check to make sure that it's reduced. Clearly it is, but we should at least make mention that you should check that first, although it's irrelevant in this case. And then you could solve this by factoring. Okay. Now let's find those end behaviors. What situation are we in here? Case 1, 2, or 3? What's the degree of the numerator? What's the biggest exponent? 1, x to the first. And what's the degree of the denominator? 2. So this is case 3. So this means that, we have a y equals 0. Asymptote or end behavior doesn't. We'll find out in a second here, actually. Zeros. How do we find those? Is the numerator set equal to 0? And then we have the y-intercept. How do we find that? Just plugging 0 in for x, right? And then I'm not even going to bother doing anything for the removable discontinuity since we didn't do any reducing. We can't possibly have created a removable discontinuity. Everybody feel good there? Wowzers, that's a lot bigger than I thought that was going to be. All right. So we'll start by writing in those asymptotes. Probably should make these tick marks not red if I'm using red to draw my graph, huh? And let's see, I got a 0 here. And I got a y-intercept around here. Everybody cool? Okay, to complete the sketch of my picture, I need to figure out, is the graph doing this or this? Which way is the graph going at these asymptotes, right? So what I would do is I'm going to do f of negative 2.1 and then f of negative 2.01 and see if it's getting bigger or smaller as it's getting closer on the left-hand side, and that'll tell me what's going on here. And because I am efficient, I'm going to use my calculator to generate this stuff for me pretty nicely. So I'm going to type it into the graphing piece, exit out of there, go to vars, yvars, function, y1, just so I can type it in like in function notation. So it's -7, so that's down below. And as I get a little bit closer, it gets more negative. So I am sure at this point that it's going to be doing that. Everybody cool? Why? So I'm bounded by the horizontal asymptote or that end behavior at 0. And I know it should be going down as it's getting close to the left-hand side of that asymptote. Sydney? Sure. Now I'm going to do the same thing to the right-hand side of that asymptote. So like 1.90 or -1.90. And then -1.99. So there it's getting further up as I get closer to it. So I know I'm going to be doing this, going through the y-intercept, through the 0, and then I need to know whether it's going to be curling back up or continuing on down. So I'm going to do another test there. So let's do positive 1.9 and then positive 1.99, and it's getting smaller, so it's going to be going down. And then the last piece is whether I have one up here or one down here, right? So we'll do the right side of that asymptote now. So 2.1 and then 2.01. So it's getting bigger as I get closer to it. So I must be up here. And you could confirm this by looking at the graph on your calculator, right? But don't really need to do that, as I could have done all this. Everything I've done here I could have done without the calculator. It just didn't feel like plugging the numbers in and evaluating by hand, because that was just going to be really tedious. So I used the calculator to shortcut it. But I could do this for sure with like a 4-function calculator. Never look at that graph at all, right? Let's do another. Okay. So again, what do we note before we get started here?
It's reduced.
Yeah, it's all the way reduced, right? There's no more reducing we can do in addition. Okay. So vertical asymptote, what do I do? Excellent. And then the next thing we wanted to do was the, what did I say? End behavior comes next, I think. What's the degree in the numerator?
1.
And the degree in the denominator?
Also.
Okay, so that was case 2. So it's going to be the leading coefficient of the numerator over the leading coefficient of the denominator. So just -1. My zeros are, how do I find those?
Set y equals 0.
Numerator
Yeah.
equal to 0. So that gives me 2. And then I need the y-intercept. And that's just, we're plugging 0 in. So if I do that, I get 2/3. And then again, since there's no reducing, we can't possibly have had a removable. So I just put a little X there or whatever. All right. All right, so I have 1, 2, 3, and there's that guy. And I have -1. So I have this fella here. And then I have 1, 2. I have that guy there. And I have 1, and I have like that guy there. Everybody cool? So I can see right away that unless I have to cross an asymptote, that piece has to be right like that, right? There would be unlikely that this would be like turning to go down and crossing that horizontal piece there. So I'm going to just make that assumption. Everybody cool with why I was able to assume that? Just seems unlikely to be the other case. So I only really need to check one spot, and it's whether I should be my arrow should be pointing down or up here on the left-hand side of that vertical asymptote. So I'm going to do it the same way I did before. I'm going to do this the efficient way. So I have 2, just update that to 2 minus x, and update that to be x plus 3. Get out of there. And we're going to do, so I need like -3.1 and then -3.01. So 51, or -51, and then more negative. So it's pointing down. And I can just whoop. There we go. Everybody feel okay doing that? Notice that I don't give like 2 poops about the actual points anywhere other than like the zeros and the y-intercepts. I'm not actually plotting points. I'm just kind of figuring out which way the arrow should be pointing at the asymptote and using the asymptotes as my guide. All right, one more example here. Okay. Vertical asymptotes. Well, before I do that, what should I do? Yeah, make sure it's reduced. So maybe I do a quick factoring check there, just to make sure that there's not any hidden reducing in there. So multiplies to give me -5 and adds to give me -4 is -5 and 1. And obviously that doesn't reduce, right? Since none of the factors are the same. So no reducing to do there. Now, the end behavior, what's the degree in the numerator? 2. What's the degree in the denominator? 1. So this is the polynomial division one. Unfortunately, you probably have to do this as a long division problem and not a synthetic division problem. I guess in this case we could do it as synthetic division, but I'm going to do it as a long division one because all we need is like, you know, if you had a degree 3 on top and a degree 2 in the denominator, synthetic division can't be done. Or if we had a leading coefficient of 5 or something in the denominator, now synthetic division is like, requires a lot of updates to make that work. Probably just easier to do the polynomial division all the time. All right, so we start by asking ourselves, what times x gives us x squared? X. So that multiplies to both places. and then we subtract down. So x squared minus x squared is 0. Negative 4x minus 2x is negative 6x. This is the place where most students are going to make their mistakes, just goofing the negatives and forgetting to distribute. Please be careful when doing that. I'll bring that negative 5 down, and then I'll repeat the question, ask what times x gives me negative 6x. Well, negative 6. So I multiply that to both places. Negative 6x minus 12, subtract down. Negative 6 minus a negative 6 is 0. Negative 5 minus a negative 12 is 7. So that's like my remainder, 7. Everybody's okay with that? So what I can say here is that my polynomial, f of x, maybe we'll write it in a blue or something, is equal to x minus 6 plus 7 over the divisor. So that's an equivalent expression to the one that was written. The piece that I care about is this piece. So my other end behavior happens at y equals x minus 6. So the quotient of the division problem is the piece that we care about. Cool so far? I know I buzzed through that. We're okay doing the long division? Sounds familiar, right? We did that last year. I tried to do a good job with it because I know it comes up again and again. Zeros are next. So there I'll just take my numerator, set it equal to 0. I'm going to just, since I already factored it at the beginning to make sure that it wasn't reducible, I'm going to take that factored form, right? That makes life easier. And then the y-intercept. F of 0 gives me negative 5 over 2. And then obviously there was no reducing, so nothing I could do with that. All right. So what do we have first? Negative 2. And then x minus 6. So if I wanted to make like an xy table for this, I could do 6, and then the y coordinate there would be 0, and then like 0 and negative 6. Is that okay with you guys? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Do that. Everybody cool there? Okay. I have my zeros at 1 and 5, or I'm sorry, negative 1 and positive 5. And my y-intercept at negative 2.5. And from that information, I can tell right away that's going to happen. Alex? Sure. Right? With those 3 in there inside, there's no doubts about what's going on in between. What I need to do is figure out whether I'm going to be over here or over here. And all I really need to do is check what's happening on the left-hand side of that asymptote. So again, we'll go back in here. I'll edit this to be x squared minus 4x minus 5 over x plus 2. And we need to look at the left-hand side, so let's do negative 2.1, and then negative 2.01. Getting smaller, so that tells me we're pointing down. The other end is just bounded by that other asymptote, so I'm done. What do you think? Not too bad, right? Okay. So section 14.2 is all about solving. So what we'll do is we'll just kind of talk about do some examples and talk about some different approaches you could take to do these examples. I have the things that I think are the easiest to do, but we can talk about some other things that you could do that are also, perfectly fine. Okay. Let's say we have this. We want to solve this. What would I do first? If you meant multiply both sides by x to clear the fraction, that would be a better idea. Yep. That is what Mr. Kulik would prefer doing. This leaves us just with a standard quadratic that I can move on to one side to set equal to 0. And I notice that quadratic factors quite nicely. So I get solutions of 3 and 1. However, I'm not done. When solving a rational equation, you can get extraneous solutions. So before you're done, you just need to go and make sure that when I plug these in, none of them give us a 0 denominator. So in this case, it's really easy to tell that, like, oh yeah, 3 over 3, not 0 denominator. 3 over 1, not a 0 denominator. So both of these are fine. That's, I think, the easiest approach for this problem. What else could you have done that would be acceptable? Well, you could have subtracted the x from both sides to make two ratios equal to each other, and then you could do your cross multiplication. And solve from there. That's appropriate. Not Mr. Kulik's first choice, but it works. What else could you have done? You could move everything onto one side. Make a common denominator. And then take the numerator and set that equal to 0. You could also do that. Those are the three obvious, I think, approaches to do that. Mr. Kulik's a clear fractions kind of guy because it usually makes life the easiest because the problem gets simpler rather than more complicated before you can simplify things. And you get rid of the fractions the soonest. But any of those approaches are fine, and those are the three approaches that will work regardless of the situation. Now, there's certainly situations where it might be easier to approach this in a different way. So this might be an example of one that to turn this into a ratio is pretty easy, or two ratios and then cross multiply. All you have to do is add the 6 over x plus 1 over. but I would still probably clear fractions here. And I notice the quadratic that I get here is factorable. So I get -3 and +2. Do either of those give me a zero denominator in the original equation? Nope. So they're both fine. Okay. Here is one where I think clearing the fractions is decidedly makes life much, much easier. So what would I need to do to multiply? What would I need to multiply both sides by to clear the fractions out of here? Maybe it's not super obvious, right? Well, the first thing I would want to do is I'd want to factor that quadratic, because to clear fractions, I really need to see the primes, like the prime terms. Everybody see that now? Does that help? What would I want to multiply both sides by? X minus 3 times x minus 1, right? I'm basically finding the least common multiple of everything. So when I do that, I have 2x times x minus 3 plus 1 times x minus 1 equals 2. So 2x squared minus 6x plus x minus 1 equals 2. So 2x squared minus 5x minus 3 equal to 0. So that probably factors, but I'm not really too interested in doing that long factoring method to do it. You might be able to guess and check it. It's easy guess and check, but I would just use the quadratic formula in this case, or suggest the quadratic formula. I mean, I see how it factors in my head without having to write all that gobbledygook out, but most of us probably aren't there for that. So what do I have? I have 25 plus 24, that's 49. The square root of 49 is 7. So 5 plus 7 is 12 over 4, which is 3. And then 5 minus 7 is -2 over 4, which is -0.5. What do you notice here, though? That one gives me a zero denominator, so I'll discard that solution and keep only the -1/2. What do you guys think? Now, alternatively, what would also be appropriate in this problem that would make the specific to this problem is I noticed that that the two denominators on the left are the factors for the fraction on the right. So one thing that I could do is I could make a common denominator so both the left-hand side and the right-hand side have the same denominator. So if I multiplied the first fraction by x minus 3 and the second fraction by x minus 1, that would make a common denominator on both sides. Everybody kind of see that? And if I do that, then I can drop the denominators and just set the numerators equal to each other, because if the denominators are the same for both sides, then the numerators have to be equal. And we're back at the same place I was in the previous problem. That's also appropriate, and that might be desirable if you see that situation where the factors of one side are the same as the denominators on the other side. You can think about it that way as well. It's doing the same thing. Usually I'm a clear fractions guy because you can just always do clear fractions and it's never really that bad. Sometimes it might be a little bit worse than like the simplest way of doing it, but it's never the worst way of doing the problem, which I'm usually pretty okay with. All right, let's do one story problem example. So let's say that we have this farmer and he wants to fence off this rectangular pasture, and he needs the area for that pasture to be 500 square feet. And we want to just know how much fencing we need. Or I'm sorry, the least amount of fencing. So this turns out to be a system of two equations problem. So if I have a rectangle, the area is calculated by like length times width or whatever. So I'll call that side length and that side width. And the perimeter, that's going to be the amount of fencing I need, right? How do I calculate the perimeter? Right? Length times width plus length times width. Everybody's cool with that? So this is my system. I know that this 500 is going to equal length times width. So I can say, for example, 500 over L is equal to W. So if I do that, I can say P is 2L plus 2 times 500 over L. Everybody's okay with that? And this is now like a rational function, right? So 2x plus 2 times 500 over x. And I can graph this, I don't know, let's go 0 to, well, certainly 500 is a reasonable upper bound, since the x's is representing the length of this thing, and like the longest the side could be is 500, right? Like, that seems pretty reasonable there. The area here, or the perimeter, if it's like 500 and then 501, so probably like 1,000 is a decent upper bound. Surely we know that that's not going to be the answer to the most efficient way to fence this thing in, is like, but, you know. So looks like we got what we need somewhere over here. So I'm going to do second trace, do the minimum command, and we'll just go range. I'm going to go all the way till I see the x is negative. Nope. I'll go right here at the asymptote, and I'll just scroll along until everything over here is bigger, right? So I'll just stop there and hit guess and see what I get. There we go. The minimum's at about 22.4 for my length, and the corresponding perimeter is 89.4. And then if I wanted the width also, I would just plug that back in here. So 500 divided by 22.4. So about 22.3. So what are we really noticing here? What kind of shape did we end up with? Basically a square, right? I think if we took all the decimal places, it would turn out to be exactly a square. The rounding is what kind of goofed me. But that should not be a surprise, right? The most efficient, like if you want to enclose an area for perimeter, the most efficient shape you have is a square, the one where everything is equal. That's probably not super duper shocking. That was 14.2. We're going to probably finish 14 today, which is fine. We have like an extra day of review later on. No biggie. Everybody okay? Still doing good? Questions on anything so far? These things feel familiar topic-wise? Not too bad. Feels very Algebra 2-y, which is probably like, for some of us, a welcome change from the trig and pre-calc things that we've been doing a lot of. Absolutely. All right. So what we want to talk about here is solving inequalities. Now, solving an inequality, how many solutions is an inequality going to give us? Infinitely many, because, right, there's lots of x's that when I square it and subtract 4 are going to give me a positive number. Everybody agree with that? So we're always going to be getting an interval. So what I like to do is I'm going to start by finding the places where it's equal to 0. And then I'm going to draw myself a number line. And on that number line, I'm going to draw an open circle at those solutions. Why am I using an open circle? Yes, very good, because it's a strict inequality. Cool with that? Now what I'm going to do is I'm going to pick a test value on each of these 3 sections. I'll pick a test value over here. I'll pick a test value in here. And I'll pick a test value over here. Doesn't matter what the test value is as long as it's in that part of the number line. So if I do -3 squared minus 4, that gives me 5. So I'm getting a positive. I know that that is going to be positive over there. Everybody's cool? 0 squared minus 4 is -4. So I know that my function is negative on that interval. And when I do 3 squared minus 4, I get 5 again. So I know I'm positive on that interval. So my solution, where we are positive, greater than 0, are going to be those 2 sections. So I know I have negative infinity to negative 2 and positive 2 to positive infinity. So far, so good. Let's do another example. This is all we're doing in this section. It's just exampling. There's not a lot of theory stuff, so to speak, which is perfectly fine. Okay. So first step is to set it equal to 0 and solve, because I want to find out the places where it can be crossing the x-axis, changing from positive to negative. How do I solve x cubed minus 4x squared plus 4x? First thing I would want to do. Factor out an x. Good job, Enzo. You can say it louder so I can hear you. If I wasn't looking at you, I would have missed that. And the next thing I would do, I'd probably try to factor that quadratic piece that's left. Is that factorable? Multiply to give us 4 and add to give us negative 4? Yeah, negative 2 and negative 2, right? So my solutions are 0, 2, and 2. Although 2 occurring twice, I don't really care. And now when I draw these on, I'm going to do filled in circles. Why am I doing filled in? Because it's or equal to this time. Cool with that? So again, I have like 3 sections of my number line I need to test. So I'll pick a value over here, say negative 1. Pick a value in here, let's say 1. And pick a value over here, let's say 3. And again, I'm going to use I'm going to type this into the graph first so that I can just do that like y1 or y1 of whatever. And it just saves, I think, some button pushing as far as I'm concerned. So if I do y1 of negative 1, I get a negative. So that section I know is negative. If I do y1 of positive 1, that is positive. So that section in there is positive. And then y1 of 3 is positive. So again, we're looking for when it's less than or equal to 0. So that's the only section I care about. But that's not entirely correct. I also have to include that single number there, because it's also equal to 0 at 2. Oh, Mr. Kulik. So sneaky. Yeah, you know, why would I not give you the sneaky ones, and or at least some of the sneaky ones before you have to go do the stuff. All right, one last example and we'll call her a day. Oh, I lied. 2 more examples and we'll call her a day. I was going to say, I thought I was surprised I didn't have a more complicated example beyond this one. Okay. There's actually 2 things I care about here. I don't care about just the zeros. I also care about the discontinuity. So I'm going to take the numerator, set that equal to 0. That'll give me a 0. And then in this case, I know there's a vertical asymptote. That's my discontinuity here at negative 1. So when I draw my dot here at here, because it's a or equal to, I'm going to use a dot. But here at -1, it's going to get an open circle. Why is it getting an open circle even though it's greater than or equal to? What is the value of that function at -1? It's undefined, right? Remember, at the asymptotes are always going to have an open circle. Your discontinuities are always going to be an open circle, regardless of what kind of inequality you have, because the function isn't defined there. It's not part of the domain. Everybody's cool with that? Okay, so we have to pick something from this section, something from this section, and then something from this section. And actually probably don't need the calculator to do this. So that's good. I plug -2 in, that's going to be -6 over -1. I'm sorry, yeah, -6 over -1. So that's positive. If I plug 0 in, that's going to be -4 over 1, so that's negative. If I plug 5 in, that's going to be 1 over 6, so that's positive. So I have those two sections that I care about. I have to be a little bit careful with my parentheses here, though. So -1 to -2 with a parenthesis there, union, bracket 4 to positive infinity. Notice I'm using the parenthesis because I used the open circle at should be -1. And I'm using a bracket at 4 because I had the filled circle there. All right, you ready to get real weird now? I am. Let's get weird, guys. Let's get weird. Let's get weird. All right. Oops. Okay, what are we going to do? Let's find our zeros. Anybody need any explanation why the zero's at -4 there? Should be able to just kind of look at that by inspection. If you want to solve, that's okay too. How about here? What's x have to be here? Just 1. Does the absolute value matter here? No, not for the solving part. Now, technically, you're like, wait a minute, Mr. Kulik, wasn't this supposed to get 2 solutions? Well, yes, technically, you're supposed to get x minus 1 equals 0, and then x minus 1 equals -0. But shoot, -0 and 0 is still the same thing, right? So just x equals 1. Don't worry. Mr. Kulik didn't skate past anything there for you. Let's -4, 3, 2, 1, 0, and then 1. Okay. Since this is a strict inequality, I know no matter what, whether it's part of an asymptote or a 0, they're going to get open circles. So I'm just going to write those as open circles. My test value here is at -5. I'll pick my test value here at 0, and then here at 2. If I plug -5 in, what do I notice happens immediately in the numerator? I'm taking the square root of a negative, right? What happens there? We're just undefined. Not positive, not negative, undefined. That's bad also, right? So no answers can come from over there. That's fine. If I plug 0 in, I get 2 over absolute value, square root of 4, 2, over absolute value negative 1, 1, so that's a positive there. If I plug 2 in, I have square root of 6, whatever that is, some crazy decimal, over absolute value of 2 minus 1, so 1. So that's positive also. So my solution then is going to be those parts. I heard it too. I don't know. Somebody was tapping probably on that door because they're like, why can't I just come in the middle of the day through that door?
There's a class out there.
You want to go check the door? Sydney, you can be the hero. Or not. You could be like, Mr. Kulik, I don't want to get up, get bent. You go do it. And I would have been like, all right, I'll go do it. It's not that big of a deal. So then I would write negative 4 to 0. Oops. I'm sorry, negative 4 to 2, and then 2 to positive infinity. Notice that I had to break that into 2 intervals because of the open circle, right? Let's stop here. Congratulations, we finished all of chapter 14 in one day. I guess next time we'll finish all of chapter 12 because I know that's a one-day section because it's all calculator. We might even be able to do 13. I'm just kidding. We're not going to do 13. I already wrote the exam. I'm not adding more stuff onto it at this point. We'll just have an extra day to kill. I'm okay with that. You guys looked panicked for just a second. You're like, wait a minute. No, please no. 13 I could not do in a day, even if I tried. Yeah, probably for the best.